Hi, welcome back to my channel. And for today's video, I don't have a plant with me right now, but I'm gonna show you something in this photo that I have a pretty dwarf sensation. Okay, and for today's video, we're gonna talk about the isomorphisms of linear transformation. So before I'm gonna start with the discussion on isomorphisms of linear transformation, I would like to give thanks to people who have been supporting me with this channel, and finally I was able to provide a lot of engagement, and I hope you all have been supporting me throughout. And thank you also for those who are new to my channel. Please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. If you have any clarifications on specific video in math, then just kindly put down your comments on the video below, and then you can also request a specific topic that you would like me to discuss. Okay. Okay, so let's start now. So we have isomorphisms on linear transformation. So let me introduce the definition here. And I hope you all have already watched about my discussion on the basic introduction to linear transformation. So this time, I'm gonna introduce to you definition for introducing the isomorphism. So given that you have a mapping F from B to W, and that is a linear transformation, then number one, F is said to be monomorphism if F is one-to-one function. So regarding on the discussion of about one-to-one function, I already have done a video for that. So kindly check the video. Okay, here's the thumbnail of the video. I have uploaded in my YouTube before, and F is said to be epimorphism if F is onto. So onto also, I have discussed that on the video, on the same video I have uploaded before in YouTube. And number three, F is isomorphism if it's bijective, or in this case, it is both it is both one-to-one and onto. Okay, that's it. So this is now the formal definition here. Um, so again, you have a mapping F from V to W. So remember, in this case, this is a linear transformation F. And also take note that V and W are vector spaces. So number one, we can say that F is, we call that one as monomorphism. Okay, monomorphism. In this case, if it is one-to-one. Okay, now F is said to be epimorphism if F is onto, and it's isomorphism if F is both one-to-one and onto. So in other words, it's isomorphism if it's monomorphism and epimorphism at the same time. Okay. Okay. So with regards to this definition here, given that your F maps from V to W, so provided that if your F here is an isomorphism, okay, so that means we're actually getting in touch on the connection between V and W. So if we can only say here, we can say here that V and W are isomorphic So in this case, we write V is isomorphic to W if we can find such mapping. So we can find such F maps from V to W that is isomorphism. That's it. Okay, so let's consider an example. In this case, the vector spaces. Let's consider this one here. So these two vector spaces are isomorphic. Why? Because you can find a mapping F here from this one to this one, and this mapping is actually isomorphism. Now, um, what is this, by the way? This F sub n square bracket t is actually of the form like a polynomial. So that means this is here, this set here is actually the set of the form a sub 0 plus a1t plus up until a sub n t to the n. Okay, so where this a sub I, your I from 0 to n, are actually element from the field F. And of course, your t here is a variable. Okay, now, um, how does that look like? So, f to the n plus 1, this is actually a vector form wherein it consists of, it's an n plus 1 tuple. So that means you have a sub 0, um, a sub n. So it's like a1 up and a sub 0, a1 up until an. So it's an n plus 1 tuple. Okay, so the reason why f sub n square bracket t is isomorphic to f to the n plus 1, it's because if you have this mapping f from f sub n square bracket t to f to the n plus 1, this such f is actually isomorphic. So to see that, I'm gonna define what this f all about first. So this is defined by this one, by sending an element of f sub n square bracket t that's equal to the n plus 1 tuple. So there are n plus 1 tuple. Okay, in this case, let's double check if this is, of course, a linear transformation. Okay, so say for example, let's double check. Um, you have a sub 0, a1t plus up until a sub n t to the n. That's the first element, so that's gonna be f of this one plus, okay, another element from f sub n square bracket t, I'm gonna assume b sub 0 plus b1t plus up until b and t to the n. Okay, now let's see if this will result to something like, remember the definition for showing that a mapping is a linear transformation is that if you are given with two elements x and y coming from the domain, you can have the result like this. Okay, now observe that this one I can have this as, I can combine a sub 0 and b sub 0, and I would have a sub 0 plus b sub 0, and then I can combine a1 and b1 here. Okay, so I have a1 plus b1 t plus up until, I also have an plus bn t to the n. Okay, sorry. By the definition of your map, this is equivalent to having a pair of a sub 0, b sub 0 plus a1, b1. I'm sorry, it's not plus here. It's a comma here because it's an ordered tuple, and then up until an plus bn. Okay, now I can split this ordered tuple. I can have a sub 0, a1 up until an, and then I have b sub 0 up until bn. Okay, this is actually the f of a sub 0 plus a1t plus up until an t to the n plus f of b sub 0 plus b1t plus up until bn t to the n. Okay, so therefore condition 1 being a linear transformation is satisfied, but we're not done yet. We need to assume first a scalar which is coming from f. Okay, so let's assume that r is an element of f. Okay, and in this case, I'm gonna have f of r times this one. Okay, and remember, I have ra sub 0 plus ra1t up until ran t to the n. Now, if you notice, r is a scalar. A sub i's are actually scalar, so they're actually coming from the field. Now, remember, the field is actually closed under multiplication, so which means to say that r a sub I, okay, in this case, r a sub I is also element of f. Okay, because r is an element of f, a sub I is an element of f, so the product is closed, so it's an element of f, meaning to say that these corresponding coefficients of the variable t sub t to the I from 0 to n, are actually elements of the field f, which means to say that I can write this as this one. Okay, and I can extract r from this. And so this is r f of the element here. Okay, so the condition 2 is satisfied, meaning to say that your r here is a linear transformation. So the next problem that we're gonna tackle is this a monomorphism? Now, okay, so let's assume that f of a sub 0, a1t plus up until antn equals f of b sub 0 plus b1t plus up until bntn. Okay, so let's assume that's equal. So meaning to say this is the same as, I can write this as I'm gonna let this entirely as a sub 0. I'm gonna let this entirely as b sub 0. So I have f of a sub 0 minus f b sub 0 equals 0. Okay. So which means I transfer, so I add both sides by negative f of b sub 0. And so I get that equation. And then f of a sub 0, or entirely this thing here, this is equivalent to a sub 0, a1, plus, up until an, and this is b sub 0, b1 up until bn equals 0. Okay, I can just simply transfer this one here, and this a sub 0 equals b sub 0. And so, therefore, f here is actually 1 to 1. Meaning to say that the corresponding a sub 0 is equal to b sub 0, a sub 1 is equal to b sub 1, something like that. Okay, now since your f here is actually defined as this one, okay, so since that is defined as this one, what happened is, since we can express f this one to this one here, and if you notice, these elements here are actually the entries of this vector here are actually elements of the field, and the corresponding coefficients here of the given polynomial here is actually coming from the field. It simply tells us right away that f here is onto, which means to say that since it's onto, it's epimorphism, and finally we can jump into conclusion that f is isomorphism. That's it. Okay, so let's double check another example. Um, the vector spaces C and R2 over R, are these two isomorphic? So let's try. Let's consider a function here from C to R defined by this. Okay, let's see if this f here is an isomorphism. So first things first, we need to double check if f here is a linear transformation. Now, if you can notice here, I have f of, let's say, a1 plus b1i, and I also have a2 plus b2i. So which means to say that these are two elements here coming from your C. Then by operation of complex numbers, so which I have explained that on my previous video about complex numbers, this is equivalent to a1 plus a2 um, plus b1 plus b2i. That's it. Now, by definition, this is equivalent to a1 plus a2 b1 plus b2. Okay. Well, I can separate this here. I would have a1 b1 plus a2 b2, and this is actually f of a1 plus b1i, and this is f of a2 plus b2i. So condition 1 is satisfied. So let R be in the set of real numbers, because we're actually talking the C and R2 here. Sorry, it should be R2 over R. So I'd have R of A plus BI, and this is just the same as RA, RBI, okay, and this is actually as RA, RB, and I can extract R here, so I would have A plus A and B, and so R is equal to F of A plus BI. Therefore, condition 2 is satisfied, and so finally, we can say that this mapping here is a linear transformation. So let's it's pretty obvious here that it's already a famous result here that these two here is 1 to 1, and in fact it's on 2. I will leave you that as your exercise. You can comment down there if you have a problem or if you have any clarification you would like to know about this. Or if you know, you can discuss that on the comment section so that I would see and I would be able to explain you as well and give a comment on that. But just so you know, this mapping is actually both 1 to 1 and on 2. So technically, it suffices to show us that we just need to show this as a linear transformation. And so everything is clear, and then this mapping is isomorphism. And so the set of complex numbers in R2 are actually isomorphic. That's it. So that's all for now. Thank you so much for watching. So if you have any questions or clarification, you can comment down there so that I would know and we can discuss that thoroughly. And so far this is actually the basic of the isomorphisms of linear transformation. Thank you, and again, don't forget to subscribe so that you'll be updated on a lot of videos that I will be uploading soon. Have a great day to you.